Today we are breaking down DeepSeek-OCR 2, Visual Causal Flow by Horan Wei and the team at DeepSeek AI. For those of you in a hurry, here's the one-minute summary. This paper proposes a pretty fundamental shift in how vision language models process images. It's moving away from that rigid raster scan of order, top left to bottom right, and it introduces something called DeepEncoder V2. It's a new encoder that dynamically reorders visual tokens based on semantics, sort of like how a human eye would scan a document. They achieve this by replacing the standard CLIP encoder with a compact LLM-Q12-0.5B, actually acting as a vision encoder. And with a special causal flow attention mask, the model gets state-of-the-art results. It hits 91.09% on OmniDoc Bench V1.5 using a max of only 1,120 visual tokens, which matches Gemini 3 Pro's budget. They've basically shown you can get 2D image understanding by cascading two 1D reasoning structures. Welcome to AI Paper Podcast. Let's get into the details.
It's great to be here. Yeah, this paper is a really interesting one because it goes right after a basic assumption that I think we've all just been running with for years.
Absolutely. And I want to start right there with the problem they identify, the status quo. We're all so used to how VLMs handle images. You patch them up, you flatten them, you scan them, row 1, row 2, row 3. Why do they argue this is fundamentally broken?
Well, the spiral analogy they use in the paper is just perfect for this. If I give you a piece of paper with a spiral drawn on it and I say, trace it with your eyes, you're not going to scan it like a printer, right? From top to bottom.
No, of course not. I'd follow the line.
You'd follow the line. Your attention moves causally. Where you look next depends entirely on where that line is going. Raster-scan it completely ignores that reality. It chops the spiral into a grid and breaks the whole continuity of the thing.
Right. A spiral is a simple example, but this problem must get exponentially worse when you move to the focus of this paper, which is documents.
Exactly. I mean, documents are messy 2D spaces. You've got multiple columns, tables, images with text wrapping around them. If you try to force a raster scan on, say, a 2-column PDF,
oh, it would be a disaster. You'd read the first line of the first column, then jump straight over to the first line of the second column.
You get a word salivus, as they call it. And we've just been hoping that the big LLM decoder at the end is smart enough to unscramble that egg.
So we're just relying on self-attention to fix a problem we created in the first step?
That's the whole inductive bias issue. The scan forces the model to assume that tokens next to each other in the grid are related. So the DeepSeek hypothesis is, what if we fix the order before the decoder even sees the tokens? What if the encoder itself could do some causal reasoning?
Which brings us to their big solution, DeepEncoder V2. And looking at the architecture, this isn't a small tweak. They did a full component swap.
A pretty aggressive one, yeah. They took out the old CLIP-style vision encoder and dropped in a compact language model, specifically Qwen 2.5B.
An LLM as a vision encoder. It feels a bit counterintuitive, doesn't it? LLMs are for text.
It sounds that way on the surface, but if you think about what a transformer is, it's really just a sequence processor. It doesn't actually care if the tokens are words or image patches. The whole reason they chose an LLM architecture is for that causal reasoning. LLMs are built to predict the next thing in a sequence. That's exactly the skill you need to, trace the spiral.
Okay, so they want the encoder to be auto-regressive, how it looks at the image. But you can't just feed raw pixels into Qwen 2. The sequence would be gigantic.
Correct, and that's why there's a vision tokenizer right at the front. It's based on a SAM-base model segment, anything, plus a few convey layers. Its whole job is just compression. It gets a 16x compression rate, which brings the feature dimension down to something manageable, 896, before it even hits the main encoder.
Okay, so we have these compressed visual tokens going into the Qwen 2 encoder. This is where it gets really clever. They talk about a dual-stream attention mechanism or a hybrid mask. Can you break that down for us?
Yeah, this is absolutely the secret sauce. So picture the attention matrix inside the transformer. They basically split it in two.
Okay.
On the left, you've got all the visual tokens from the image. For these, they use standard bidirectional attention. Every token can see every other token.
Like BERT or a normal vision transformer, which makes sense. You want the model to have that full global context of the image to start with.
Exactly. But then on the right side of the matrix, you have what they call causal flow queries. These are special learnable tokens. And for these, they use a triangular causal mask.
So like GPT.
Just like GPT. Here's the rule. A query token can see all of the visual tokens, the whole image, but it can only see the query tokens that came before it. It can't see into the future of the query sequence.
So it's a hybrid. The perception part is global, but the processing part is forced to be sequential.
Yes. Think of the queries as a series of glances. Query 1 looks at the whole image and decides, okay, the starting point is the title. Then Query 2 sees the whole image and sees that Query 1 picked the title, so it decides, all right, the logical next step is the first paragraph.
It's building a logical path through the image step by step.
It's forcing the encoder to construct a narrative. And they mention in the paper they actually tried to do this with a more standard cross-attention setup, like you'd see in BART.
And it didn't work.
It didn't just fail, they said it failed to converge, the model couldn't learn. They found that for this to work, the visual tokens and the queries have to be in the same block, interacting at every layer. They call it a prefix design.
So the encoder's final output is just those reordered query tokens. It throws away the raw visual tokens.
That's right. The encoder only passes on the query tokens to the final LLM decoder. It's essentially acted as a translator. It converted a 2D mess into a clean 1D logical sequence.
Let's talk about the token budget for a second.
Yeah.
So you're seeing these massive context windows on models like Gemini 1.5 Pro. How many tokens is DeepSeek actually using here?
It's surprisingly lean, actually. They use a multi-crop strategy. So they take one global view of the image, which generates 256 query embeddings.
Okay, that's the baseline.
Right. Then, if the image is complex, they can take up to 6 smaller, high-res local crops. Each of those adds another 144 tokens.
So the maximum is, what, 6 times 144 plus the 256?
Which comes out to 1,120 tokens, maximum.
1,100 tokens. I mean, that feels incredibly low. Some dense vision models are pushing 4,000 or 5,000.
It's very efficient. And they point out this is right in line with the budget for Gemini 3 Pro. The argument is about token quality over quantity. Because these tokens have already been reasoned over and sorted by the encoder, they're much more semantically dense. The decoder just doesn't need as many of them.
The heavy lifting is already done.
Exactly.
Okay, moving down the pipeline to the decoder and the training, they kept the decoder the same from DeepSeek-OCR V1.
Yep, no changes there. It's a DeepSeek-3B mixture of experts decoder, about 500 million active parameters. I think they wanted to isolate the variable, you know. If the model gets better, it's because of the new encoder, not because they bolted on a bigger brain.
Makes sense. But the training pipeline is new. It's a 3-stage process. Can you walk us through that?
Sure. It's pretty clever, designed to kind of bootstrap this whole causal ability. Stage 1 is just encoder pre-training. They take the vision tokenizer, the new Qwen 2-based encoder, and they attach a really lightweight temporary decoder. They just train it on 100 million image text pairs to teach the encoder the basics of seeing.
Just general feature alignment.
Right. Then stage 2 is query enhancement. They toss the temporary decoder and plug in the real DeepSeek 3B decoder. They freeze the tokenizer, the SAM part is already good, and train the encoder and decoder together. This is where the model really learns that causal flow.
Aligning what the encoder outputs with what the LLM expects to read.
You got it. And then stage 3 is decoder specialization, and this is the really smart engineering part. They freeze the entire DeepEncoder V2. The whole vision system is locked. They only train the final LLM decoder.
Why do that?
Speed. The paper says this doubles their training speed. Since the vision encoder is the most computationally heavy part, freezing it lets them just churn through data way faster to fine-tune the LLM on interpreting those specific query tokens.
That's a great little detail. It shows they're thinking about production and training efficiency. So let's get to the payoff. The numbers. They ran this on OmniDoc Bench V1.5, which is a pretty tough benchmark. How did it do?
It did really, really well. The top line score was 91.09%.
91%. And the previous version was what, in the 80s?
The V1 model was at 87.36%. So that's almost a 4-point jump. In OCR benchmarks, that's not an incremental gain, that's a leap. But the really shocking part is the comparison to other much larger models. It beat Qwen 2.5 VL72B.
Wait, it beat a 72 billion parameter model?
It did. And remember, DeepSeek's total active parameters here are around 1 billion total. It also outperformed Gemini 2.5 Pro, which was at 88.03%.
Wow. Okay, so that's a huge validation for the architecture.
Yeah.
But there's one metric you pointed out to me that I think is the real smoking gun for their whole theory, the reading order edit distance.
Yes. This is the one that proves the point. Edit distance usually measures typos, right? How many characters you have to change. Reading order edit distance measures if you got the sequence right. Did you read the columns in the right order? Did you mix up the caption with the main text? Their score dropped from 0.085 in V1 all the way down to 0.057 in V2. And lower is better.
That is a massive reduction in ordering mistakes.
It's huge. And it proves the performance boost isn't just because of, better feature extraction.
Yeah.
It proves the causal flow hypothesis is correct. The model understands the logical structure of the document way better than the old raster-scan baseline.
And this has real-world benefits, too. They mentioned a drop in the repetition rate.
Right. Anyone who's worked with these models in production knows this pain. When a VLM gets confused by a layout, it can get stuck in a loop, just repeating the same sentence over and over. In their online user logs, that repetition rate dropped from over 6% down to just over 4%. It's a big gain in stability because the causal queries are giving the decoder a reliable map so it doesn't get lost.
I want to zoom out for a minute and talk about the philosophy here. The paper uses this phrase I love: 2 cascaded 1D reasoners.
This is the big conceptual shift for me. For years, we've been trying to solve a 2D problem by just throwing 2D data at a 1D model and hoping for the best. DeepSeek is basically saying, let's stop pretending. Let's break it down. Step 1 is a 1D causal reasoner, an encoder. Its job is reading logic reasoning. It turns the 2D map into a 1D path. Then step 2 is another 1D causal reasoner, the decoder. Its job is task reasoning. It turns that path into text.
So you're decoupling the where to look problem from the what does it say problem.
Exactly. And because both parts are causal, they speak the same language. The encoder thinks first this, then that. The decoder thinks first say this, then say that. It just removes all the friction.
They also hint at this being a step towards native multimodality. It's not just for images.
Yeah, that was a fascinating little tangent at the end. Because the encoder is a standard Quen LLM, the parameters themselves are generic. They suggest you could use the same encoder weights for audio. You just swap the vision tokenizer for an audio tokenizer and use audio causal queries.
So one brain to organize all the sensory input.
It moves us towards a unified omnimodal encoder instead of having these bespoke, separate encoders for every single data type.
A true one transformer to rule them all situation. You just change the front door.
Precisely. It simplifies the entire stack.
Before we wrap, I want to touch on their future work section. They had this really provocative thought about what you might call System 2 thinking in vision.
Oh, I loved this part. It really connects to what we're seeing with chain of thought in text models. They point out that right now, the number of query tokens is tied to the size of the image. But for a really complex task, like analyzing a dense scientific diagram where you have to look back and forth between the chart and the legend, a single pass might not be enough. They suggest that maybe for some tasks, you need more causal flow tokens than you have visual tokens.
So the model needs to think for longer than it sees.
Exactly that. Imagine an encoder generating, say, 100 query tokens to describe an image that only has 50 patches. It would be conjuring the image, running internal reasoning loops to figure out the structure before it even hands the result to the decoder.
That completely blurs the line between perception and reasoning.
It does. It suggests that seeing isn't just a passive input process. Seeing is a reasoning process. And if that's true, future encoders will need to be autoregressive thinkers themselves. We're moving from computer vision to, visual reasoning.
That is a wild thought to end on. The idea that your vision system needs to think before your brain even gets the full picture. Well, that's all the time we have for anyone who wants to get into the weeds, and I really recommend checking out the code for that hybrid mask. The weights and the source code are all public on the DeepSeek AI GitHub.
It is definitely worth a look for anyone building VLMs. It's a very, very elegant solution.
Thanks for listening to AI Paper Podcasts. We'll catch you on the next one.
Goodbye.